Hi everyone, and welcome back. We're going to try a kind of a strange problem this time, and then we're going to calculate the unit edge cell length for a solid solution. So we're going to have 85 weight% iron with 15 weight% vanadium. And all that vanadium is in a solid solution, and it's all at room temperature, and the crystal structure for this alloy is BCC, bi-center cubic. Now, the big important thing here is we're going to have to realize, like, if we have this BCC cell. Okay, so here we go. Let me try to draw it. I'll do my best here. One in the back, one over here, one in the front. Beautiful. And I also have that one in the middle. And any one of these could be vanadium. Now, they're mostly iron. There's 85 weight%, but some of these are going to be vanadium. And so, we're trying to get the edge cell length. We're only going to be able to figure out the averages. Okay, we can only find it on average. We can't just pick one in particular. We could. It would be super easy if we did. I'm just going to choose, where iron is like this and vanadium's there. Done. I'm easy. We're going to be looking for averages. Now, that's all fine and dandy. But if we're going to use an average unit cell length, well, we're probably going to have to use average other things as well. For example, we're going to need to find out the atomic weight average. And we're also going to need to find the average density. These are all going to be things we're going to need to solve this problem. Okay, so let's bounce down here and start working at it. First off, an equation you can find in your book, if you want to, is the following. You can find out the average density is equal to N times the atomic weight average all over VC times Avogadro's number, where this is the volume of a unit cell. Now, we're trying to find that cell length, so luckily we can just place this with a cubed and not worry about any radiuses. So average is going to be equal to N times the atomic weight average all over a cubed, that's the unit cell side length, cubed, times Avogadro's number. Now we want to solve for A, so we'll go ahead and rearrange that and say that A is equal to the third root of N atomic weight average over the density average times Avogadro's number. That's the third root. If you don't know how to put that in your calculator, you just do caret to the 1/3 and make sure that's in parentheses, with everything else in front of it being in parentheses. Things like that. Now we know a whole lot of this. For example, our average weight and our density average, that's just a weighted average. We're going to be bringing in our atomic percent for all of these. So it would look something like the following. For my atomic weight average, it would be equal to 100 over the percentage in weight percentage of iron over the atomic weight of iron plus the percentage of vanadium over the atomic weight of vanadium. And it would look something like this. If I plug everything in, I would get the following. I'm not going to bother plugging all these numbers in because I'm just going to do it in my calculator at the end. There we go. Oh, forgot to put the number in. So this weighted average kind of formula, you're going to see it a whole lot. We're actually going to use it twice in this problem, so you need to find the density average as well. So the density average, very, very, very similar. It's going to be equal to 100 over the concentration of iron over the density of iron plus the concentration of vanadium over the density of vanadium, which if I plug all that in, I get the following. So now I have my atomic weight average and my density average. The only thing else I need to figure out is what is N. Well, N is the number of atoms per unit cell. And we know that for a BCC cell, there are 2 of them. So this will be different for a simple cubic and different for a face-centered cubic and hexagonal close packed. So I plug everything I just got into my equations, and I get a huge monster, which I'm not even going to bother to plug in my calculator. If you don't know it, Avogadro's number is 6.022 times 10 to the 23rd. Be very careful plugging all that into your calculator, and you will get 2.89 times 10 to the negative 8 centimeters, which is equal to 0.289 nanometers. And that would be the average. Average is the key word here, unit cell length. It's not saying that every side would have that, but on average, that's what you would see. So, thanks for listening. I hope this helps you. Do not, under any circumstances, forget this weighted average formula. It's very, very helpful. And I will see all of you next time. Bye-bye.